Here we are at acceleration part 2. So in the last one, we sort of learned that acceleration is any sort of change in velocity. So, average acceleration equals any change in velocity which occurs over a change in time. This can be handy if you know what the average acceleration is. You can actually predict different velocities at different times. And that becomes really handy with things like gravity or rolling down a hill, which is also gravity, or sort of going down a slope of sorts, because gravity is always a constant acceleration. So what we can do, though, is we could say, I know that I started off at zero velocity, and if I'm rolling down this hill for this amount of time, I'll know my average acceleration. So how fast will I be going at a given time period? And stuff like that. So if we were to rearrange this equation a little bit, let's see, we could pull the time over here. So it would be average times the change in time equals the change in velocity. And we know that the change in velocity is actually velocity final minus velocity initial. So then what we could do is we could take this velocity initial and throw it over here. So we can end up with the average acceleration times the change in time plus the initial velocity equals the final velocity. So in this sense, what we could do is we could solve for final velocity, and hopefully you can see that this is just a derivative of this original equation right here. And we do a lot of that in physics, where we're just taking this one equation and we sort of morph it out a whole bunch of different ways. So let's go ahead and look at an example real quick. All right, let's say that, let's come up with a scenario. Let's say that we've got a guy and he's running across a freshly oiled ice patch. Okay, and so the problem with running across a freshly oiled ice patch is that you tend to fall. So here's our guy right here. I'm running. Here's his shoes. All right. So what should we call him? Let's call him Tommy. That's a good name. So you can imagine Tommy is a super athletic guy, so he gets a long way. And so Tommy is running on this freshly oiled ice patch. And the reason we have a freshly oiled ice patch is because we don't want any friction to be involved in this problem right here. And so let's say that Tommy is running along. Let's say he works himself up to a velocity of 2 meters per second, right? So Tommy's going at 2 meters per second, and let's say that he falls, and so here's falling. Here's his feet. Oh, that's his head. Arms, head, very large neck. All right, so he falls right here at the base of this slope, which is also freshly oiled ice patch. And so let's say that then he'll continue, of course, up the slope, but as he goes up the slope, he's going to have a constant acceleration that's going to slow him, which is 0.50 meters per second squared. Okay, so this is his acceleration to slow him. So let's see how fast Tommy would be going after 2 seconds. So let's take our equation that we learned. Velocity final equals velocity initial plus acceleration times time. Now, I just sort of simplified that a little bit from what we saw before, but this is exactly the same thing, so don't freak out. All right, so here we are. So what is his final velocity? So we know his initial velocity is 2, and we know his acceleration is 0.50. And we're hoping to find out how fast he'll be going in 2 seconds' time. So there we are. That's t, not plus. And so if we go ahead and solve that, one thing that's very important is that this acceleration is slowing him. So this is going to be a negative acceleration because it's going opposite to his initial direction. So it's going to subtract from his initial velocity. So remember, we always have to include these as vectors, and so this is where some of that comes into play. So it's a negative acceleration because as he's going up the hill, we know that he's going to be slowed. Okay, so if we go ahead and solve this out, here we go. That's going to be 2 plus negative 0.5 times 2 is going to give us a final velocity of 1 meter per second. There we are. So after 2 seconds of sliding up this hill, this slope, he's going to be going 1 meter per second. So let's say that we were to imagine what's going to happen to him as he goes up. Well, he's going to continue to slow down. Eventually, he's going to get to 0, right? But he still has that constant acceleration, and so that acceleration isn't going to change to 0. The acceleration is going to continue to accelerate him to 0, and then it's going to just essentially move him back down the other direction. So let's say, okay, we want to see what's happening to Tommy at 6 seconds. So let's go ahead and do our final velocity equals, so we've got our initial velocity is 2 meters per second, and plus we know that our acceleration is in the negative direction of 0.5, and we want to see where we are at 6 seconds. So multiply this all out, we end up with negative 1 meters per second, okay? So there he is. He's coming back down the hill in 6 seconds. He's sliding back down the hill at 1 meter per second in the opposite direction. Thus we have the negative 1 meter per second. So this equation you can solve for velocity anytime that you know if you have any sort of constant acceleration. So like I said, this becomes a very, very handy equation to use anytime you're looking at anything to do with gravity, because you know that gravity is always going to cause a constant acceleration. So if you can figure out what that is, it's a little bit different on a slope, of course, than it would be just free falling, but free falling is always going to be a constant acceleration of 9.8 meters per second squared. So that comes in handy there. Or if you're just told the acceleration and they want to know how fast you're going at a certain time. All right, so maybe some more examples to come, but that is motion with constant acceleration and solving for final velocity.